Yeah, so I thank organizers for inviting me to this conference, and I think for the last lecture we all deserve a little entertainment, so it will be not completely mathematical lecture. Yeah, and the main idea the main idea from today will be try to retell the usual saga of motives using only non-commutative words, in a sense. It's like Ramon Queneau, exercice du style. I have restricted language and repeat the same story and see what goes on. And Pierre will see that many of his ideas are relevant in different places, and also he probably will be interested to know that wave conjecture is not proven yet. It's only in some special case of commutative varieties. Yeah, but it's a very special case. Yeah, but in fact, it's not even formulated properly yet. So it's okay. Yeah. So what is the plan? My talk. I think you can see it. Yeah. Yeah. So I'll have some kind of 4 parts. First, I'll give you a very short introduction to non-commutative algebraic geometry, and this kind of version of non-commutative algebraic geometry is a very simple one. So the old definition we'll see in 10 minutes. And it doesn't really deserve the name geometry, but let's call it that. And then I will give some examples of what's called saturated spaces. The name is not perfect. It's something like smooth projective variety. And probably one should find another more emotional name. And then I will describe algebraic Derm cohomology and closed relative Hodge homology. And at this point, will be some conjectures will pop out, many conjectures. So I will try to say what a non-commutative version of pure Hodge structures. So it will be something called complex numbers. Then the definition of categories of pure and mixed motifs. And then will be periodic story with some conjectures for L-functions. So I now go from this side. So it will be, I'll speak about this non-commutative algebraic geometry in derived sense. Okay, so this subject, I don't know if it's really focused. Oh, yeah, it's better. Yeah, this subject was started, at least from my perspective, by Alexei Bondel in early 90s, but definitely Mukai transform was very relevant. Yeah, so the non-commutative space in this kind of geometry is a small triangulated category. So it's the same story. And all this business is very convenient to put extra x in the category is Karoubi closed. So any projector gives a completion direct sum. So it's supernatural. And the category will be, as used to be these days, to be appropriately enriched in the most kind of fundamental way enrichment to have spectra underlying homes from each object, so that usual homes for shifted objects are negatively graded with respect to index homotopy groups. Or one can have complexes of k-linear vector spaces. And in this case, we say that space is k-linear. And today everything will be k-linear for some field, and at the end will be R-linear, where R is a ring. One should construct some kind of cofibrant complexes of R modules, which means something technical. You consider finitely generated projective modules and add more and more such things. Such a differential of new module lies in the previous modules, kind of inductive limits. Such. Sorry. Okay, so plan. Suppose. So the next definition is of what has some chance to be related with algebraic geometry, or maybe some infinite dimensional geometry. And I say the space is algebraic over field if it's described by some differential graded algebra. So what does it mean? So I consider category differential graded A modules, and it can be yeah, one should be really technical here. One should consider something like infinity morphisms, and so it's a big category, and inside this category is one object, algebra itself, and then one can construct the smallest possible triangulated category which contains this object. So add shifts, cones of morphisms, and because I ask about Caribic closeness, you add also direct summons for when you meet new projectors. Yeah. And why it's relevant to algebraic geometry, there was a recent theorem, maybe 2 years ago, by Bondal and Alexei Bondal and Michel van der Berg, that if you get a scheme of finite type over a field, then it's algebraic in this sense. I mean that the category of perfect complexes can be described by this one algebra. And how to, in other words, what they proved, it's the same story, is that consider category of perfect complexes, this is the split generators, again, in Karoubi sense. So any sufficiently big vector bundle or complex vector bundle will generate the whole category. So there's not only one algebra, there are many, many algebras, but all of them are derived Morita equivalent, so the same category of perfect modules. And so in a sense, you see that schemes are affine spaces. They describe by just one algebra. So in this derived non-commutative geometry, there's no this things like Zariski spectrum, gluing, topos, nothing like this. We get just one big algebra, and not so big. And in fact, the first example is a classical work by Sasha Bellinson, that projective spaces are affine. Namely, you consider algebra, consider projective space of dimension n, and consider direct sum of first n plus 1 powers of ample line bundle. And consider endomorphism group ring of this vector bundle. There's no higher x, so you get just ordinary finite dimensional algebra. Take opposite to it. And this is a theorem is that bounded derived category of coherent shifts on projective space is the same as perfect complexes. The same thing for this algebra A. There are many other generators, but it's one of the simplest. Okay, so this I think we can dispose. Yeah, and here are two basic definitions about this algebraic non-commutative space. We say that the space is proper if this algebra as a complex has total finite dimensional homology. Algebra which describe any of algebras, it's independent choice of algebra. And the second definition, that the space is smooth if algebra is perfect as a bimodule of itself. Namely, one can make tensor product of algebra tensor opposite, and algebra will be DJ module, and in the appropriate triangulated category should go to perfect envelope of this A times A opposite. Yeah, so that this thing doesn't depend on choice of generator, it's an intrinsic property of a category. And for schemes of finite type, it's just equivalent to usual properness and smoothness. Okay. Yeah, so what is this smoothness? Yeah, so there are kind of 3 types of examples of smooth algebra, not necessarily proper, which means not necessarily finite dimensional thing. Namely, you can start with smooth affine. I'll give example of smooth algebras in degree 0, not differential grade algebras. So the first example is algebra function on smooth affine variety. Then it has finite resolution, kind of Koszul resolution for affine space. Or it could be free algebra with finitely many generators. Or it could be some kind of quantum group story. Yeah, so that's essentially 2 basic definitions. And then one have 2 simple properties for me, the easiest way to define them is through kind of infinity language, but I don't want to bother you today with this language. First of all, if you have this proper schema in this sense, the finite dimensional homology, then not only algebra is finite dimensional, but X groups between any two objects form a finite dimensional space, because essentially construct in finite way from algebra. And you'll have canonical bilinear form on K0 of the category, the earlier characteristic of R homes from one object to another. And this bilinear form is in general neither symmetric nor skew symmetric. And the formula for this R common examples is kind of Riemann-Roch formula in a sense. Yeah, and what is another point that in this case, because homes are finite dimensional, in a sense you can write a modulo space of all objects. The claim that the precise language is in some kind of geometric infinite stacks, as Carlos explained, but kind of in most naive sense, one can say the following. This set of isomorphism classes of object, maybe I should assume the case algebraically close here, is this set of k points in a countable union of some schemes of finite type, but some schemes are formal. And the formal thickening of some just schemes. And equivalence relation is of similar nature. You have some countable union of varieties mapping to the square of this guy. Yeah, and sorry? Formal, yes, yeah, it will be such thing differently exists, yeah. Maybe no, maybe you're right, I'm not totally sure. No, I think the formal comes from the second thing. Namely, if now consider the smooth proper spaces up to equivalence of under category, then it will be k points, and here it's really need formal, yeah, you are right. So in principle, one can write computer program which will work infinitely long, but at the end of the day will produce a whole classification of such things. So
what are morphisms between non-commutative?
It's something to discuss. I'll tell you. Yeah, I'll tell you. Yes. Yeah. So the name for this thing, kind of smooth and proper, for today's lecture, I choose the name saturated because it's essentially equivalent to kind of small refinement of the notion of saturated categories introduced by Bondel and Kapranov in the early days of this subject. For them, it was a category which has enough objects that any functor is representable, but that means saturations. That's kind of good spaces. Yeah, that's the meaning. Yeah, so there are several things which we can do with these saturated spaces. If you get first basic operation, which is kind of trivial in commutative case, you go to opposite category or opposite algebra. And then you can go to tensor product. You just multiply two spaces. It's not categorical product. It has nothing to do. It's not inner product in a category. It's not, but just some symmetric monoidal structure. And then you can combine these two things in obvious way. Consider kind of bimodules, left and right bimodules. And these are called maps. For two spaces, you get space of maps for this saturated space. And these maps, one can, the old definition of this smooth and proper was designed for this thing that maps are functors from one category to another. Objects on this category of maps are functors, and the category of functors is endowed with the structure of triangulated category by this means. And finally, there is some operation which I actually will not need today, but it's most mysterious part of the game. It's a gluing. If you get a functor or map from one space to another, or in other languages, a bimodule, then I construct a new space. Sorry? A map is object of this category. Yeah. It's a functor, yeah, it's the most obvious thing. And so if functor is given by bimodule, you construct a new algebra of triangular matrices where bimodule sits in one corner and algebras on diagonals. It's again an algebra. And in some kind of philosophical sense, gluing is analogous to taking cones in triangulated categories. And projective space, so this theorem of Belinson about what projective space made is equivalent to algebra, it also has another incarnation. The projective space, it's actually glued from n+1 points. You interact, you have one point and glue to this another point and so on. And what was one of great things is discovered about this gluing, that as the braid group acts on the iterated gluing. So if you have category constructed iterated gluing from some pieces, then you can apply element of the braid group and represent the same category as iterated gluing of the same things, but maybe in different order. And finally, there is some very simple duality theory, which also was found by Alexei Bondel, that for any saturated space X, you get canonical map from to itself. It's called Serre functor. It's closely related to Serre duality, but it's not a Serre duality. Namely, it's defined by the following formula. If you consider home from one object to another, it's finite dimensional space, or R home is finite dimensional. Then I take dual space, it should be kind of again representable functor, and it's home from S to something applied to E. And in the case of schemes, it's you calculate it easily. This Serre functor is multiplication by canonical class, so top volume forms, shifted by dimension. And it's completely intrinsic object. Okay, so now we have this saturated spaces, and what are examples of such things? And we can list the whole list. Yeah, so there are several sources. You can start with smooth proper schemes. But also it could be not necessarily scheme, but art in algebraic spaces or Deligne-Mumford stacks and a smooth proper. Then we can associate to these things a non-commutative saturated space. Sorry? Maybe. Yes, you're right. Here's the group cohomology. Yeah. I think I will make several mistakes, so please correct me. Yeah, so it's characteristic 0. So locally take cross products for a finite group acting on algebra functions, and it will be a local model of such things. Or more generally, there's another kind of similar version. You take a smooth proper scheme and Azumaya algebra, kind of bundle of matrix algebra. Then you also consider modules of this matrix algebra and get good category. So there's a big class of examples coming from deformation quantizations of smooth projective variety. Suppose you get a variety with algebraic Poisson bracket, and I want to construct a non-commutative space. And the general procedure is the following. You consider ample line bundle, kind of O1 in whatever, in projective embedding over X. And in order to quantize the variety, you need lift Poisson bracket to the total space of this line bundle minus 0 section. So it's L minus X is this C star bundle or JM bundle. And you should have Poisson structure, tangent space to this total space of a line bundle. And the Poisson structure should be homogeneous of degree 0. Also assume that for my original variety has vanishing first and second cohomology with coefficients with a structure sheaf. And its birational invariant property holds essentially all reasonable examples because usually varieties are rational, which one quantize. Yeah, and then the construction from such data, one can construct canonical quantized space. It will be actually a graded algebra of sections of power of line bundle one can quantize as a graded algebra, but it will be non-commutative. So in local coordinates, the product will be, the space will be on a field of Laurent series in variable h bar, Planck constant, and the product is for usual function is usual product plus h bar times the Poisson bracket, one pair Poisson bivector field with product of differential functions and so on. And in this case, one can construct without reconstruct Fagan-Adesky elliptic projective spaces. Also, one can quantize del Pezzi surfaces and things like this. In fact, these elliptic spaces belongs to another realm as well. This Arten, Jean, Tate, van der Berg, non-commutative projective spaces. And these are also examples of saturated spaces. Yeah, so there are several. What's
the rule of the
to have projective to have graded ring. Yeah. For example, there's actually important example. If you start with K3 surface, it has a algebraic symplectic structure, but it cannot be quantized in any reasonable way because there's no line bundle will have such business. You can have quantization of formal power series, but not. Will have not enough objects in this category. It will be not really algebraic, or there will be no resolution of diagonal in the definition of saturated space. Yeah, and now I'll go to this my main playground for making guesses and hypotheses. It's a new class of categories, and it's called Landau-Ginzburg models. The name came from topological string theory from B model. Yeah. So first of all, I just want to kind of extend the previous story. One can speak about Z2 graded non-commutative spaces. Namely, it's a category with isomorphism of functors, shift by 0 and shift by 2. And all notions which I explained, the really few notions, algebraic, smooth, and proper, extend to Z2 graded case. And for proper, for example, the definition is that not that cohomology are finite dimensional, but zero cohomology plus first cohomology are finite dimensional because they are two periodic. Okay. Then suppose I get a map from smooth scheme over field to affine line, just function. And the idea is that it gives a Z2 graded space, which depends on X and F. It's a pair. Kind of informally speaking, it's the following. I deform space X by some element Hochschild cohomology. And I use function and element of zero homology, which is even number. And I deform by this not 2 cycle, but 0 cycle Hochschild homology. And the description of this category is the following. So the original definition through the deformations gives a description as a kind of matrix factorization problems. And it's easy to describe kind of locally. Globally, one should need some cluing. Locally, if my spaces are fine, what we do, we consider supervector bundles on X. So we have two components, a 0 and a 1, and a kind of fake differential, a map of all modules, which is odd map, goes from A0 to A1 and back, with square equal not to 0, but multiplication by function. But you ignore the problem that square is not 0 and pretend that its square is 0. And then want to define what is home between two such things. Namely, you consider homes between these two supervector bundles, get infinite dimensional supervector space, And you write the differential which you expect to write in the case when d squared equal to 0 and d f squared equal to 0. So I get this differential on map from E to F, and the square of this thing will be 0 because the commutator is F, which is central element. So this whole story works for arbitrary algebra and any central element. Yeah, so it's one description, and globally, Dmitry Orlov found some different description. So I assume here that function is not identically 0 on any component of my space. Then the category is quotient category in usual Verdier sense, with enrichment, so on. You consider hypersurface Z, the preimage of 0, as a subscheme. It can have nilpotence. An interesting example, kind of in one variable, f is x squared or x cubed. And so it gets a subscheme, and consider bounded derived category of coherent sheaves on this Z, and it contains perfect complexes. And it's not the same thing because Z is singular. And to take quotient category, and it is naturally two periodic. And it's the same thing as this matrix factorizations. No. No, I said just spaces. They're not, I will just go to this thing. Yeah, and so this kind of major unanswered question in this subject, it seems it's very natural to expect that this category is saturated if the following sets, not this whole the map is proper. It's enough to have this set of critical points if function has value 0. It's one of components of critical set is proper. And the whole category depends only on small, actually formal neighborhood of x0. In fact, not only formal neighborhood, but something up to finitely many Taylor coefficients. Yeah, so one can replace x by formal thickening. Other critical values play absolutely no role in this category. And so Orlov proved that in case of when function has rational singularities, or Z set has rational singularities, but this seems to be true in general, but probably we just need some extra idea. And the simplest case of such gadgets is series of isolated singularities of functions. If we have analytic functions on Cn with isolated singularity at 0, it's of course not algebraic, but it's up to some change of coordinates can make algebraic, and that's an example of such thing. Point is proper, and you get some nice category. Okay. So, for quadratic singularities, one get very important category. One get modulus of some superalgebra, which is kind of analog of division algebra in superworld. You get some odd variable xi with xi square equal to 1. Yeah. That's yeah. Now we go to cohomology series of general non-commutative spaces. So suppose first I have ordinary unital associative algebra. Then there is something called homological Hochschild complex. It's negatively graded. The formals are completely standard, so I don't need the formals. I just, if anybody never saw him, that's how they look like. And it has some version which is some quasi-isomorphic version which is quotient complex. You on all factors except the first one, we are mod out by unit in the algebra. Now, so this is something I don't fully understand what is it, what it's calculated. It calculates Tor in a category of bimodules from diagonal model to itself or something like this, but I don't know. Now, so what is it in real life? If you get smooth affine variety, then this is a very old classical theorem by Hochschild, Koslant, and Rosenberg that cohomology of the Hochschild complex are forms, are differential forms, but placed in negative degrees in kind of opposite order. And it's our arbitrary field, and globally it's essentially the same story. It was in some other formulation, theorem of Czech-Weibel, but if we get a smooth scheme, but not affine now, in characteristic 0 or in large characteristic relative to the dimension, then cohomology of algebra, whatever is describing this space, is the sum of cohomology with coefficients with forms. But grading is kind of strange one. So you get cohomology for smooth projective variety totally symmetric around 0. So you get both positive and negative grading, and the whole picture will be symmetric.
What is the A?
A, it's I forgot to say that everything is generalized to DG algebra, and one can. Sorry, I forgot to say that the whole thing can be generalized to differential graded algebra, and for variety one can make some described by some algebra. Endomorphisms are home from some big vector bound to itself, and then will be this story. Yes, because a priori one can have a spectral sequence, and in the case when characteristic is smaller than dimension, it should be non-trivial, and should be some replacement for this cohomology efficiency form. The idea is that one have a map from Hochschild complex to forms and back, and have maps, but in these maps you need divide by some factorials, and there are maps in both directions. Oh no, there is a map which is quasi, I think, in one direction from Hochschild to the form, and this is a right map, and it's quasi-isomorphism with prime numbers. Yeah, so it means that we can kind of collapse words and define for non-commutative space Hodge cohomology as Hochschild homology of algebra, like it looks for usual schemes. And there is some intrinsic definition in terms of category of this Hodge cohomology of space, and for saturated space, it's the same as maps for homes in the category of maps or endofunctors from identity functor to Serre functor, which I introduced some time ago. Yeah, and now we go to the idea of non-commutative geometry of Alan-Kohn. So what is the RAM differential in forms? Yeah, it is called Kohn operator, some capital B, which has square equal to 0, anti-commutes with differential in Hochschild complex, and has degree -1, so it goes in opposite direction. And in order, and here I really introduce complex, otherwise things will not work. No, I define by this formula, but that says identity is only in reduced complex. And the formula is some standard one. You take, again, sequence of elements of the algebra. You apply all n+1 cyclic permutations, and in the front put identity of the algebra and take sum with signs. Yeah. So in the case of a smooth affine scheme, this induces a de Rham differential on forms which are cohomology of this previous complex. Yeah, I just said that everything generalized to DG and Z2 graded algebras, and right definition in general is this sum. Yeah, so you get notion of forms and differentials in a sense, and then we go to periodic cyclic homology or cohomology if you treat space of algebra. And this is the following. I introduce some variable u of degree +2 in the graded case, or just even variable, and consider formal Laurent series of my complex Oh, I need to extra break. Ah, no, here it is. Yeah. Of my complex with a thing and with differential d plus ub. So use kind of small letter. We slightly perturb differential d. Yeah. You can ask why I consider only a Lorentz series. Maybe I can consider formal Taylor series. It also will play a role later. But this thing is module over Lorentz series, and because u is in the graded case, you can multiply by u. You see the things are periodic with period 2, and just you get two things. HP in period. You get Z2 graded vector space associated with the X. And for smooth scheme, again, the same assumption on characteristic, you can calculate it and you get sum of all even and odd de Rham cohomology group. Yeah, so it's analog of non-commutative analog of de Rham cohomology. And then you get obvious, because it's perturbation of cohomology, you get dimension of cohomology can only go down, you get finiteness. For saturated space X, this HI, this Hochschild homology have finite dimension because it's something inside, again, compact space. And you get perfect complex, you get finite dimensional rank for Hodge homology, and also rank of periodic homology as module over Lorentz series could be only smaller than this is. Oops. Yeah, formulas I will not really need. So just sorry. Yeah, so this main definition, I say that for algebraic space, the spectral sequence from Hodge to de Rham collapses the first term if the following holds. It's kind of infinite sequence of finite statements. For any positive integer n, let's consider truncated polynomials in variable u with the same differential d plus ub. And this property means that it's free module or flat module over truncated polynomials. It has no torsion, the cohomology of the complex. And for saturated X, it's kind of obvious that it means that here, in this inequality, you get equality. So the rank of de Rham cohomology is equal to rank Hodge cohomology. Yeah, so reduced complex means I divide by ones. Yeah. So now there's obvious guess what we should do by analogy with usual algebraic geometry. For saturated X over field of characteristic 0, the spectral sequences should collapse, because it's true in so many examples. Yeah. So it's true for schemes and for quantum deformations, so deformation quantization for stacks, Alzheimer algebras, and for Landau-Ginzburg models as well, in the Z2 graded case. And there are two types of proof. So this is a kind of almost commutative situations all. And there are two types of proofs in all cases. One is through Keller geometry, and another is through finite characteristic or periodic method, like Faltings and Deligne started 15 years ago. And for Keller geometry, I have absolutely no idea what does it mean in non-commutative derived setting. So it probably should be some new idea, but it looks that there is a good chance that this finite characteristic method works in non-commutative case. So I will tell about this later. Yeah, so we have this conjecture about collapse, and now let's assume this conjecture and try to get what structure will appear on cohomology. First of all, I would like to define this cohomology of complex over Taylor series in variable u. It denotes its by h sub u. And it will be super vector bundle because I assume that it's 3 modules. So it's sections of, I would think, the supervector bundle. And then this cohomology has sections of the supervector bundle. So the next story, it's a bit difficult to explain with explicit formulas. On this supervector bundle, one has canonical connection outside of 0. And it's easy to explain in Z-graded case. In Z-graded case, this complex is Z-graded. So it means that we get action of multiplicative group, which multiply lambda in the field, multiply u by lambda squared. And this gives essentially it gives a connection with logarithmic singularities at 0 with eigenvalues of residues half integers. And the monodromy of the connection will be identity minus identity on even and odd part of cohomology. So you get first order pole, and it's essentially filtration by half integers. In filtration, it's kind of closed non-commutative relative of Hodge filtration. It has only one index because cohomology lose the index. Filtration and maybe it's with low index A, so it will be increasing filtration as you like. To consider fp of h n DRAM for all possible values n and p, such that a is half integer and n over 2 minus p is alpha. Yeah, so it means that in this non-commutative geometry, cohomology lose weight. So there's no notion of fate. You cannot distinguish Tate motifs from trivial things. So only index p minus q in cohomology matters. Yeah, what happens in Z2 graded case? It's kind of a generalization of the thing. In Z-graded case, it's reduced to this previous story. They claim that there's a connection on this bundle, and the formula, I have some explicit formula, have something like 5 ugly-looking terms. And but there is, so I don't want to show you formula; it will take too long time. But the explanation is roughly the following: for this non-commutative algebra, there's notion of Gauss-Manin connection. If you have flat family of algebra, then on periodic cyclic homology, when you invert variable u, you get a flat connection. It was constructed by Ezra Getzer's extremely complicated formula, which I don't understand yet. But then you apply to the next remark. In Z2 graded case, you get for each algebra, you get automatically one parameter family of algebras. It's very strange. It's kind of renormalization group flow acting on Z2 graded spaces. Namely, suppose you have differential graded algebra, and I have non-zero parameter lambda. I want to introduce a new differential graded algebra. It will have the same underlying vector space, the same parity, the same product, but differential will be multiplied by lambda. And it's not isomorphic to itself as a degree algebra. It's isomorphic to itself only if algebra is Z-graded. Yeah, so you get some non-trivial flow. Fixed points are Z-graded things, or something maybe fractionally graded things. Yeah, and then you get this family, and you consider Gauss-Manin connection along this family. And it's easy to see that to move along this family is the same as multiply variable u by a constant. So you get some formula, and explicit formula shows that you get connection with second order pole 0, not first order pole, but second order pole. Yeah. Also, there's a special thing, but it will be not really relevant. Maybe for one remark, that you automatically get also a pairing between fibers at opposite values, fiber 2 and fiber minus u, up naturally paired, and this pairing is not degenerate and goes up to u equal to 0. So it means that Hodge homology it also has non-degenerate pairing. This pairing is covariant, and in general is not symmetric on isosymmetric. It's related to this bilinear form on K0, which I told you before, restricted case. Yeah. So get all this beautiful structure with this spectral sequence collapse. If it's not collapse, you get something with torsion and kind of ugly, but I hope things don't exist. Yeah, so this explains that in Z2 graded cases, connection has second order pole, and example suggests that it still have regular singularity. So it means that under some transformation with Laurent coefficients, you get first order pole. And then one can speak about monodromy for such things, and the monodromy should be quasi-unipotent. So all eigenvalues are of residue and will be rational numbers. Yeah. So what happens in for Landau-Ginzburg model, which for me is the main test case for all this story? So I assume this constraints that critical points where function takes value is proper set. Then the section of this bundle can be described in purely classical terms. You consider hypercohomology of the variety with coefficients in the following things. You consider here we don't take care about Z grading. It's that is a Z2 graded object. We consider a sheaf of forms and take formal power series in U with coefficients of the sheaf, and differential will be U times D dRAM plus dF. And I don't remember. Yeah, if I just remind you, in this formula, and I have it here. And all my formulas, the differential is D plus UB. B is dRAM differential, and D is kind of multiplication by dF. So it's similar to this formula. Sorry? It's even graded, but we have to forget about it. Yeah. Yeah, so it's D plus UB in certain sense. So it means that you kind of consider non-algebraic expression exponent of function over U and consider the RAM cohomology. It's also U. Put it here. And there are now 3 proofs of the degeneration of Hodge to the RAM spectral sequence. It first was proved by Sergei Barannikov and myself using harmonic theory and for kind of a version of Simpson-Hitchin correspondence, but the details of this proof seems to be completely lost. So but it's kind of assumed to be a theorem. So it wasn't published, nothing here. And yeah, there were some talks, and then Claude Sabat listened about this thing and gave a different proof using Saito-Hodge modules. And a couple of years ago, Vadim Vologodsky and August provided a proof in style of Deligne-Luzy using lift mod p square, things like this. Yeah. So that's all the story. And so in my next transparency, I will give you an application of this collapse, when it can be used. And actually, it was for me main motivation to believe in this collapse. Namely, so it's just some construction. I will not tell you about this construction. It's too long story. Which can be thought as kind of algebraic B-module or generalization of Pierre's conjecture on cohomological operations in cohomological Hochschild complex, about which I'm not talking today. So what's the input of the construction? We start with saturated Z2 graded space, such that spectral sequence collapse, and the space is Calabi-Yau of even or odd dimension. The meaning of the thing is the following one. There's a Serf functor which is tensoring by canonical class and shift by dimension, and in geometric situation. So we say that it's isomorphic to identity functor or pi identity functor. So dimension is even or odd, and canonical class is 0. Yeah. So assume that such thing happened for your category or space. Then we can make choices. I mean, we can first trivialize bundle with respect to the pairing which I mentioned. There was some pairing. So identify everything as a fiber at 0, and pairing should be constant. And also I should use isomorphism between, here's the existence of isomorphism, then I should choose isomorphisms between Serf functor and identity functor, even or odd, with high homotopies, because Serf functor has some symmetry built in, so it would have infinite tower of homotopies. And eventually one can say it's empirical homological data. One doesn't need all high category business. Namely, one should need a linear function on the section of the bundle. Oops. Maybe, oh, I have a mistake. Maybe go to negative powers of u here. I think I made a mistake here. Something related with cohomology satisfying some non-degeneracy condition. Yeah, in a usual case, for usual Calabi-Yau variety, what means first? First means that you split Hodge filtration in a way compatible with Poincare pairing. The second means you choose volume element on your Calabi-Yau. And output is a cohomological two-dimensional field theory in sense of our work with Manin many years ago, which was encoding of Witten's ideas. So I get finite dimensional spaces, Hodge cohomology of X, and for any stable moduli space of stable curves, I get a map from this h to power n to beta cohomology of this moduli space. So it's not actually, yeah, it's kind of fake to algebraic. It's not algebraic variety for me. It's combinatorial topological object because I go from the RAM cohomology to beta. Now, so that think. Now I'll go to the definition. What is non-commutative pure Hodge structure over complex numbers? So the definition, which it looks at the moment, is the following. It's a holomorphic supervector bundle. So it has even one part over, let's say, neighborhood of 0 in complex numbers. Flat connection with second order pole. If you like, it can have regular singularity, but in fact, it's not obligatory things to have regular singularity. And you get some lattice, and you have a local system of finitely generated abelian groups, Z2 graded outside of 0, which kind of topological case theory depending on parameter u. Set it outside of 0. If you complexify it, you get this vector bundle with flat connection. It's analytic data. Yeah. So that's a Hodge structure. And the main problem, how should we define this lattice? The answer is clear in all almost commutative examples in Landau-Ginzburg model. And what is the idea for this lattice? So it's kind of really wild guess. And I have no idea what to do in Z2 graded case, so I'll describe Z graded case now. The idea is the following. If you have complex manifold, we can have something like C infinity manifold associated with this. And the project is if we have non-commutative space, then we have another non-commutative space, A prime, which will describe kind of nuclear algebra, Fréchet algebra, I don't know what else. And we have a map from C infinity space to complex space. So pullback of algebraic function is C infinity function. And we need three properties from this. Does this map induce isomorphism on periodic cyclic homology? The case theory of this soft space X prime has both periodicity. So it's like for C-star algebras and things like this. And should be Chern character from case theory of this space, should be finitely generated lattice, such that it, well, Chern character exists on all these frameworks. The case theory should be sufficient lattice, should be lattice in cohomology. Now, so in the scheme, if I consider the algebra of functions on this manifold. Yeah, I have to warn there are many possible X prime. For example, there is Fourier-Mukai transforms. There are different algebraic varieties with the same as non-commutative varieties. Equivalence of derived categories are abundant, especially in Calabi-Yau case. So you get completely non-diffeomorphic varieties. And so this A prime is in no sense unique. So yeah, and here one can use the following. What happens for C infinity manifold? In fact, if calculate, yeah, here probably one need to calculate periodic homology with some kind of continuous, because algebras belong to functional analysis realm. So periodic cyclic homology of X is the same as the rank homology. It's like this Horst-Rosenberg theorem. It's a fine case. And the image of K0, the K0, it's topological K0, is essentially integral homology, but you multiply by 2 pi I to power n in Hn. And then, if I think about it, it means that for K1, you should introduce this bizarre factor, square root of 2 pi I, which is, and Kohn has it in his book. In fact, so it means that this lattice, if you want to something compatible with both periodicities, then it's completely inevitable. For example, image of K2 will be the same lattice multiplied by 2 pi I. So to make really one lattice, one should normalize properly. And so it means that for odd numbers, we should multiply by this highly transcendental number square root of 2 pi I. And it means that, for example, periods for such varieties are kind of normalized to have weight 0 in a sense. For example, if calculate number 2 pi I will never appear as a period for this variety, or integral of holomorphic one form will be divided by square root of 2 pi I, and so forth, so on and so forth. Yes, I put everything to weight 0 artificially. Yeah, so that's the idea where the lattice should come from, but it's a big analytic problem. Yeah, and now there is one can formulate analog of Hodge conjecture. So this, let's consider this saturated space, kind of smooth projective variety, and then the image of K0 of this algebraic variety in sections of the bundle by chain characters, like Holmes from identity. This map obviously one to Holmes space. In the category of non-commutative Hodge structures, as I explained, should be isomorphism. Yeah. Actually, what here goes on, and in my definition, I explained that HU is bundle of a formal power series. But while speaking about germs of functions, the connection has a regular singularity, and then it means that one canonically extends from power series to small disk. And lattice is this theoretically lattice. And there was a simple result we proved with Lyudmila Katsarkov that for Landau-Ginzburg model, this is not a new conjecture. It's just ordinary Hodge conjecture. Using this description of the category and so on, one can reduce, in resolution singularity, one can reduce to the usual Hodge conjecture. Yes. Next story is Yes. Yeah. It's not really formulated. No, conjectures are not really formulated, I'm afraid, in this stage. Yeah. So then also one can define a notion of theory of polarizations for such Hodge structure. So suppose we had non-commutative pure Hodge structure, which for me means a bundle, a neighborhood of zero connection, and as a lattice. And polarization will depend on some real number which is called radius. Maybe it has some physical meaning. So it's the following. It's polarization. It's something. First, the data doesn't depend on the notion of radius. It's isomorphism between Hodge structure and dual to opposite. What does it mean, dual to opposite? You can opposite Hodge structure correspond to opposite algebra, and if you analyze the story, it means that you go from variable u to minus u. You make this reflection. And dual, we consider dual spaces, dual lattices, dual connections. So it means that you get a pairing between opposite fibers at u minus u, which goes integral on lattice and goes well on 0. And then this should satisfy symmetry and positivity constraint. I'll explain in a moment what does it mean. This symmetry and positivity depends on radius. So it's close to this idea of Pierre, which Carlos Simpson explained. Goes to twistor bundles, but this extra twist of twistor bundle. Namely, suppose we have the following situation. We get a holomorphic vector bundle over CP1 and a pairing between, let's consider involution without fixed points, kind of central minus r squared divided by u bar. Here's radius enters the game. And suppose we get holomorphic pairing between h at u and h at conjugated sigma of u for all points u to C. That's easy to imagine, such story. But now imagine that bundle is holomorphically trivial. So it's sum of copies of O. It's just vector space everywhere. Then it means that this thing is holomorphic things on trivial bundle should be also constant. And you get some pairing between vector space and complex conjugate. And we assume that this pairing is Hermitian, symmetric, and positive definite. Yeah. So that's this story. And how this thing can be constructed, this bundle from this Hodge structure with polarization in the small circle will be the same as our bundle. And pairing on the boundary when absolute value is equal to r, when involution acts, is given by this my complex linear pairing together with complex conjugation. And complex conjugation associated with the lattice, which comes from real structure coming from the lattice. So it's a natural notion, and the recent paper by Claude Sabat implies that it implies that in Landau-Ginzburg model there exists a polarization for all sufficient small radii. Precisely speaking, he was interested in different situation. We get a global proper map, and then we get a bit larger cohomology. We get other critical values, not zero. And the picture is that for small radius, the contribution for all the rest is exponential. Small one can throw it away, and you get things. And one can also kind of conjecture an analogy with usual geometry. It's a photo-rated things polarization should exist. And polarization is coming from this pairing, and if you analyze it, it should be Chern class of some endofunctor. But endofunctor, I have no idea what is it. It's my first guess was it's multiplication by ample line bundle, but it's not as easy. You need something like lambda operation as well in cohomology, and it's not a thing which comes for free. Yeah, so some. Yes, it was on the web. This was web about Fourier transforms of whatever, of variation of pure Hodge structures, things like this. Yeah, yeah, and why we need these polarizations? The application is the following: if there exists a polarization on the cohomology, then it implies that the image of K-theory of plus Hodge conjecture. Yeah, sorry, it's all full, very optimistic science. Yeah, then the image of K0 in cohomology is quotient by numerical equivalence. And what's numerical equivalence? It's like analog of Cho group. Numerical equivalence is the following. I remind you this is bilinear form, earlier characteristic of R-hom in K-theory, which was not symmetric and not antisymmetric, and it has a left and right kernel. But this kernel is the same as follows from Serre functor. So the kernel does depend on side you choose, and you get this quotient group. And then one immediately gets the definition what is a pure motives for any field. Now we optimistically jump from zero characteristic to all characteristic. Yeah, so it's Karoubi envelope of some effective motives. It's like Grothendieck definition. So objects are the spaces, and homes are K0 space of maps, modular numerical equivalence. So pretty simple definition. And all previous conjectures imply that this is semi-simple rigid tensor category. Yeah, so this are pure motives, and the corollary is that we get a pro-reductive group. Actually, supergroup, but some non-commutative motivic Galois group. And how it's related to usual motivic Galois group. So for usual motives, in this framework, we do not distinguish state twist from original motives. So we consider kernel of motivic, usual motivic Galois group responsible for pure motives to JL1, representation in Tate motive. Let's consider kernel of this. And representation of these things are non-commutative varieties which come from commutative world. But there are other things. And so this group X maps here in this non-trivial kernel. And kernel is, maybe no wrong word, there are definitely some things in the kernel. And there are representation of things which don't factor through the story. Like Anderson proposed many years ago motives related with values of gamma function at rational things. And you get kind of Hodge grading P and Q with P plus Q integer, but P and Q are rational. And in my non-commutative world, this sum is not relevant, only differences interesting for me. So, yeah. Yeah, and then finally one can, I'm afraid Volodya Voevodsky is not present, one give kind of one sentence definition of what's a triangulated category of mixed motives. Yeah, so it's not shifts with transfers in Nisnevich topology or this horrors, it's something much simpler. So let's consider the following category enriched over spectra. Objects are the saturated spaces, and morphisms between two objects, and it should be a spectrum. And it's K-series spectrum of the category of maps. Yeah. So you get something, and spectra, as Sasha explained, it's something very similar to complex abelian groups. And it looks like we get some kind of full subcategory in triangulated category. And any such thing can be canonically extended to minimal possible triangulated category. You take triangulated envelope, we add artificially add cones of morphisms and direct summons, but finally many things. And you get this category is very close to what we expect in commutative situation, with a small difference that Tate motives is not the same. And logic is kind of reversed. And in one of standard conjectures in commutative world that X groups of motives are related with K-series, but here it's definition. So it's yeah, and in fact the same definition I've seen recently in paper by Richard Nest and somebody else on C-star algebras. If you consider all C-star algebras, these people introduce structure of triangulated category on C-star algebras. For two C-star algebras, you define Holmes as Kasparov KK theory, bivariant theory, which is roughly speaking something with compact support in one direction, and so it's very close to this. Yeah, it's different T structure. Yeah, actually this K-series spectrum is connected because there's no negative K group and for this good categories, such only K0. So it means we get some T structure which is different from what we used to have. Now, and now I go to the last subject. Oops. Okay. Okay. So it's about Frobenius isomorphism. Yeah, so the conjecture is the following: that for saturated space now we are over periodic integers. So it means that some kind of scheme with good reduction at prime. Yeah? So I don't know how to treat bad reduction, so it's about good reduction. Should be canonical Frobenius isomorphism between two complexes. I consider complex for Lorentz series as periodic cyclic homology with differential d plus ub and plus pub. And maybe I think here should probably put minus sign. I'm not totally sure. And this should be isomorphism of ZPU modules preserving connection. And I think it should work without any constraints. Like it's this theorem of Falting's describing isomorphism of between forms and differential d and PD, but it works when prime number is larger than dimension. But because the Hochschild complex and drum homology are really wrong things from non-commutative point of view, I think it's all will be repaired in this non-commutative world. And anyhow, there's no dimension in non-commutative world. Yeah. And then what can we do with this? So we get it means that identify fibers of this bundle at point U and point PU in certain sense. And then we connect it by path and use the holonomy. Holonomy is not canonically defined, it's up to root of 1, but eigenvalues so defined up to roots of 1 in these things. And I get Frobenius operator with coefficient with p, and this is Weyl conjecture, which I mentioned at the beginning, which looks much more nice, in fact. Its eigenvalues are equal, has norm equal to 1. Yeah, because there's no weight, yeah, so yeah. And there is one example which I checked. I take this Landau-Ginzburg model and function x square. And Frobenius should be this identification of those things. There's only one choice one can guess, and it will be multiplication by such thing. And it presumably gives me with minus sign. And one gives some kind of infinite series. You sum this infinite series, you get nice periodic number. Homology of finite dimension. This periodic number is fourth root of 1. And it's specified, but it's equal to p minus 1 over 2 factorial mod p. And there is some kind of explicit formula, and I talked to Don Zagier. In fact, eventually people knew it from gamma functions, periodic gamma functions. So it gets this eigenvalues of Frobenius in this case. Yeah, and why I'm so optimistic about this periodic world, it's so this observation made by Dmitry Kalendin in spring, that for any associative algebra over finite kind of prime field Z mod PZ, you get a canonical linear map from zero Hochschild homology to itself. Zero Hochschild homology for algebra is quotient by commutant, and the map is raising to power p. And I leave you as a pleasant exercise to check it's additive, well-defined and additive. Yes, it seems to be really new observation. It's very elementary, but new. And moreover, it leads to the lift from cohomology to periodic cyclic homology. So mod p, here these things will disappear, so you get Hochschild homology, and here you get periodic homology. And formula is, one can write explicit formula. So from A you go to some finite sum. A priori should go to Lorentz series, but you go to finite sum. The first term it's a to power p, and there will be a product with some extremely complicated coefficients from which I cannot make really combinatorial description. You get these terms, and it's power of u. And it's for p bigger than 2, for p equal to another simple formula. But the last term I can calculate in this formula. All coefficients are, first of all, they are non-canonical, and they are very complicated. But the last coefficient is canonical complicated, the same p minus 1 over 2 factorial. So it's non-zero. So and it actually plays important role that it's non-zero. Yeah, so what's the origin of this Frobenius isomorphism? Yeah, so I have really no clean picture here. One can make kind of two conjectures. First, that this thing is coherent module. And this is completely opposite to zero characteristic. So here it's a new space introduced polynomials in U. So before series or Lorentz series, here's polynomial. And this is completely opposite to zero characteristic case when you get infinite torsion. And if you consider punctured affine line, you get zero cohomology. This is one thing, and from experiments, can try to calculate examples. And the next is that if the next conjecture is universal, if you have differential algebra which is flat over p, yeah, it's not. Then you get canonical quasi-isomorphism between two things. Yeah, so I'm almost finished, so I'll just continue this picture. Yeah, so these two conjectures imply the generation of Hodge-Ram, and Kalendin claims that he has some proof of some version of the generation anyhow without these conjectures, but it's very technical and I'm not able to prove it. And there is some simple reason for the second conjecture, why these two differentials give the same cohomology. On C, there is another filtration, very stupid one, by how many elements of algebra you use. And on Gauss filtration, you get differentials and which are essentially of combinatorial nature by permutation in cyclic group. If you analyze the formula, in D plus B you get two usual terms in cohomology of cyclic group, and in another complex you just only one minus permutation. And the same thing is the claim that if n is coprime to P, this thing is acyclic because it's cyclic group is of order n, and we have non-commutative P, so it's calculated. And if it's equal to Kp, it's equivalent to the same thing with a difference in one direction when you divide by P. There is some kind of it's cyclic covering circled by itself, essentially nothing else. And it's canonical quasi-space, which is not trivial at all, and one should use basis, and works also not only mod P but modulo finite power of P as well. Yeah, so that was very good idea. And now the last thing, it's about L-functions finally. Yeah, so it's a simple game. So if monodromy is -1 space, like in the graded case, one probably should get L factors which normalized with these weights, and Billinson conjectures are much nice. So you get Riemann hypothesis that's all zeros on real part is equal to half, and K groups related to special values in some uniform matter. And I forgot to say that one can develop theory of mixed motives as well, and all the stories. So these things can be formulated non-commutatively. Yeah, and the last, I think it's kind of bad news. I think this all this nice story eventually produce the same class of motives as we have. Yeah, maybe it's Landau-Ginzburg story. But potential use that maybe in Lagrange correspondence one should construct non-commutative space instead of spaces, which will be easier. Okay, thank you. Okay.